Today, we continue in our sort of on and off series about how we are using things like the blend and probabilistic information to support decision support services, which of course is now the flagship, you could say, service that the Weather Service is providing for our core partners, emergency managers, and others who fit that category. It's an ongoing exploration in how the information that's coming from the blend and other ensembles can be applied to this really critical communication decision-making process. We are attempting to help our core partners make better decisions. And so there's a lot of nuance, a lot of considerations in how to communicate verbally or with visuals, when to communicate, how to basically provide the sort of staging for these folks to make better decisions, etc. So today we're getting an example from Brian Mroska, the SOO, Science and Operations Officer at the National Weather Service Forecast Office in Tampa Bay, Florida. And the topic he's going to be presenting is utilizing subtropical ridge flow regime convective precipitation climatologies within AWIPS to enhance warm season probability of precipitation forecasts and related decision support services across the southeastern United States. I'll remind everyone that our format is Brian's going to present for about 30 minutes or so, and then we'll have Q&A. We would ask you hold off your questions until the Q&A session. A reminder as well that this session is being recorded, and we'll let you know when the recording is uploaded to the VLab forum website after the conclusion of the talk. So without further ado, take it away, Brian.
Oh, thank you very much, and good afternoon, everybody. As said, I am Brian Mroska, the Science and Operations Officer at the National Weather Service Office in Tampa Bay. The title here is definitely a mouthful, but it's it really boils down to how do we do a better job forecasting and decision support with the very subtle and complex convection that we see in Florida and the Southeast United States during the summer months. So we'll start by talking about why sea breeze convective forecasting and decision support is vitally important to this part of the country. And we'll talk about the flow regime, climatology, the methodology behind this research to start off the presentation. That's what we'll talk about as part one, or the research side of this discussion. And then we'll go on to part two, which is more the moving to operations part. And that's the integration of this research into the Advanced Weather Interactive Processing System, otherwise known as AWIPS, and also the public and media-based website that's been created for accessing all these sea breeze climatologies in their various forms. So why is this research so important down here in Florida? Well, Florida's unique geography and favorable conditions, both on land and in marine, for various human activities, and then combined with the daily pulse convective type of thunderstorms we have in the summer, we're annually near or most of the time at the top of lightning fatalities and injuries in the United States. And if you look at these charts, you can see why. Looking at water-related activities, beach, boating, fishing, and swimming are round out the chart, all things that are huge outdoor activities here in Florida. Lightning fatalities, sports-related activities, almost 30% is related to golfing. Florida is one of the golfing capitals of the United States. And if you look at this chart down here in the bottom left, it's getting a little dated in terms of years, but it's still accurate in that once you get to the summer months, June, July, August, and September, that's when we see the majority of our lightning fatalities and injuries here. And it should be noted that a precipitation forecast or probability of precipitation forecast here in summer is inherently also a lightning risk forecast. Most of the convection we have contains lightning, so there's almost a one-to-one correlation there. And real quick, just want to say that this research is really standing on the shoulders of giants. It's not brand new and goes back quite a ways actually to the 70s with NASA trying to forecast windows for rocket launch windows at Kennedy Space Center into the 90s and early 2000s. Florida State University and the Florida Department of Environmental Protection put a lot of time and effort into these type of research efforts, and then into the later 2000s and 2010s to current day, the Weather Service has been trying to utilize this methodology to improve their forecasts. So we got to start where we have to start, right at the base, and that's the sea breeze. And everyone knows what the sea breeze is on a general basis. Deep refreshing breezes at the beach, wind in the sails for the mariners. But the sea breeze is not just simply an onshore wind forecast. It often leads here in Florida to a much more inclement and dangerous weather phenomenon. Anyone who lives in Florida knows a pleasant day at the beach or out boating on the Gulf can change in a very big hurry. And you go from that to this in a matter of minutes, and it can cause a lot of problems with people who are offshore in their boats and people that do not react fast enough to the changing weather conditions. So what we got to do is tackle this sea breeze thunderstorm threat from a forecasting and decision support standpoint. We have to get better at when and where these thunderstorms are likely to form. And the best way we've found is to use what we call, or it's the flow regime methodology. So let's talk about flow regimes. Flow regimes are really defined by the subtropical ridge. It refers to the specific interaction between the large scale or the synoptic wind flow and the various sea breeze boundaries. Now, this synoptic flow here in Florida during the warm season months, summer months, is controlled almost entirely by the position and the strength of the Atlantic subtropical ridge, which is, when it boils down to it, it's just a region of high pressure. It's often centered around 30 degrees north latitude over the Atlantic Ocean, but as we'll see, it does move a little bit. The ridge will shift to the north and south somewhat over time, and like any other weather system, becomes weaker or stronger. The ridge's position and strength will highly impact the weather conditions across Florida and also the eastern Gulf of Mexico, which is where National Weather Service Florida Forecast Office is covered. This variation in the structure of the ridge from day to day will play a very big role in this question of where and when for thunderstorms. So being able to forecast what the tropical ridge position is and how that will impact the weather from day 1 to day 2 and beyond, all the way out to day 7 or 8, is very important in our forecast for the summer months. So we'll go into the flow regime study methodology. The study period that was looked at was the days of June 1st through September 15th for the years 2002 to 2019, so an 18-year length study. The days within that study were classified. The days that were used in the study during this time period were classified as ones in which the synoptic pattern was controlled entirely by the subtropical ridge. Any days with synoptic patterns that had any influence from nearby tropical cyclones or rare frontal intrusions into the southeast United States were excluded from the study. And when we started to take a look at all the data, we came out with a total of 8 different flow regimes that depend on the position and strength of that subtropical ridge. And they're listed there on the bottom left with the kind of a frequency chart on the bottom right. And it's quite plain to see that some regimes are much more frequent than others. We had some in the study period that were over 450 total days, with others that were just under 100 days. So certainly some are more in tune to our summer pattern than others, but all occur each summer at least several times. So what we did is, in order to classify a day as a particular flow regime, we looked at the 1,000 to 700 millibar mean vector wind at 12Z. This is the time of day when we're most unlikely to be contaminated by convection. And that mean vector wind was then calculated within a defined zone over the Florida West Coast, denoted by the red box there. The wind data was taken from the North American Regional Reanalysis, or the NAR data, using U and V wind components at 1,000, 925, 850, and 700 millibars. The precipitation data utilized across the entire South United States came from the Stage 4 hourly rainfall accumulation data. And so we took the wind data and the resulting flow regime and this precipitation data and fed it into the graphical forecast editor, which is known as GFE, which is a Python-based computing system the Weather Service uses for forecasting. And we put those in there with our developed scripts to combine them into convective precipitation climatologies. So now we're going to look, this is going to be part 2 of our talk, looking at in the research operations phase, the Q operations part. So we're going to take a look at each one of the 8 distinct flow regimes. We're going to start by looking at the most basic data, which is the 24-hour convective patterns. So this is the probability of precipitation being measurable, greater than 1/100 of an inch, during a 24-hour period for each one of the patterns. We'll identify the various temporal climatologies that are available under 24 hours, then discover how this research is being incorporated into AWIPS to enhance forecasting and support, and again, introduce the new website housing all of the data outside of AWIPS. So we'll go through these one by one. The top is kind of a mean sea level pressure plot for all of the days that combine the study. And the first regime, number 1, is classified as light and variable flow. This is generally when the ridge axis lies directly across the center of the peninsula. So within that box of definition, our mean vector flow is 4 knots or less, so light and variable. And you can see with this pattern, we generally have 2 maximums. We have one along the west coast, which occurs fairly early in the day, and then another maximum in the middle of the peninsula. Without much of a synoptic flow, the 2 sea breezes from the east and the west coast of Florida are able to move inland at about the same rate. So they eventually collide in the middle of the peninsula late in the day, giving a second maximum. However, if we move on over to regime 2, this is when the subtropical ridge has shifted a little bit further to the north and provides most of the peninsula with an east to northeast flow at 5 to 10 knots. Quite a big difference in the rainfall climatologies between regime 1 and regime 2. With the biggest deal with this being that the air is generally a little bit drier during this type of synoptic pattern, but you can see that the maximum rainfall probabilities have come down significantly in all areas, with the highest rainfall now being brought all the way down to the far southwestern corner of the peninsula. Regime 3 flow is when the subtropical ridge moves even a little bit further north, up north of the I-10 corridor into Georgia or even South Carolina. And this presents a stronger east to northeast flow across the peninsula, greater than 10 knots. A little bit more moisture in the air now, and we're starting to bring those precipitation chances up in most places, but certainly still not where we were with the regime 1 type of climatology. The maximum rainfall probabilities with this one being down along the southeast Florida coast during the morning hours with the onshore flow. And when we get to regime 4, we're starting to reverse the pattern. The subtropical ridge comes down south, it's over South Florida or the Florida Keys. This turns the wind around, so now we're looking at a south to west flow across the peninsula at 5 to 10 knots. We really start to bring up the precipitation chances across the peninsula, maximizing them on the eastern side of the state, where the east coast sea breeze is held close to the coast by the synoptic flow, and the west coast sea breeze is allowed to move very rapidly across the peninsula and collide along the I-95 corridor. These days, you'll see around the Cape Canaveral area, up towards Jacksonville, some very high probabilities of precipitation, Well, here along the coast of the Tampa Bay area and further south, they drop off significantly, especially as you get towards the beaches. Regime 5, the high pressure is moving further south. Now we're down to the Florida Straits. This is a southwest to west flow greater than 10 knots. This is a very wet pattern for the Florida Peninsula, but it's also a rather disturbed pattern with the flow coming off the Gulf and a lot of moisture. So you tend to have very high precipitation potential, but weaker storms, less lightning, less potential for strong or severe thunderstorms, and much more fast-moving storms. Regime 6, this is a south to southeast flow at 5 to 10 knots. This is one where you really get a defined difference between the west and the east coast of the peninsula. The convective maximum is squarely on the western side of the peninsula along the I-75 corridor and ripples up the coast during the day, starting in the early afternoon around Naples or Fort Myers and ending from Tampa Bay northward after 4 or 5 o'clock in the afternoon. Well, across the peninsula over towards Melbourne or the Cape, you're looking at very low probabilities of rainfall, generally under 20 or 30%. Regime 7 is very similar to 6, with a little bit more moisture in the atmosphere, so we get slightly higher rainfall probabilities, but a very similar pattern. And then regime 8, the last regime, is a north to northwest flow, 5 to 10 knots. This tends to happen when we get a trough along the east coast, which cuts the subtropical ridge in half, and we end up with some sort of a bubble high in the eastern Gulf of Mexico. And that suppresses a lot of the higher convective probabilities down towards the southern part of the peninsula. There was a regime 9, which was the stronger flow in the north to northwest flow. However, we just could not get enough study days to classify anything statistically significant out of that. So we left it at 1 through 8. So the AWIPS integration effort, it became very clear quickly that this type of information is very useful to forecasters. And the way that the Weather Service does it's gridded forecasts, having a first guess that is rooted in climatology and rooted in some very distinct scientific rules was going to be a very advantageous for the forecasters. So again, we have 18 years of data, so it's pretty robust. All the climatologies have been converted and now stored in WMO AWIPS-friendly GRIB2 files. This allows the data sets to be ingested into AWIPS very easily, and AWIPS can process the data as just another model. These climatologies in our system are no different than the global forecast system or the NAM, RAP, etc. Just thinks of it as another model data set. We can utilize the AWIPS Data Access Framework, or the DAF, which is a Python system that allows us to grab data out of our system in any way we really want to. So by utilizing the DAF, we've written scripts that will calculate the regime day automatically for the forecaster. The utility of the GRIB2 AWIPS ingest and this DAF capabilities finally allowed for the operational expansion of this methodology to all NWS offices within Florida, and we are hoping to deliver the tools and data sets this spring and get them into their systems and working before the beginning of the convective summer season. This methodology of utilizing GRIB2 files also allows updating the data set as we go through time to be much easier and more automated. So this is just a quick look at the latest iteration of the tool that will be going out to the Florida offices. There's an automation for a first guess at the regime day and population of the forecast with the resulting climatology. So the forecaster can take a look at that and make any decisions if they need any changes. Forecasters can certainly choose to manually input the flow regime based on analysis if they want to. Some other options, it's automated or manual. The forecaster can choose the temporal period that they want, anywhere from hourly to 12-hourly climatologies. They can pick the forecast day that they would like to populate, starting from day 1 all the way up to the end of our extended period, day 7. And there's also some smoothing and rounding functions in the tool if forecasters want that. One of the newer features is the ability to combine these climatologies with in a weighted blend with the national blend of models. So we could utilize climatologies and some of the benefits that the MBA will have, maybe with increased moisture or above normal precipitable waters in the atmosphere, things like that, that will help enhance the climatologies up or down for a particular day by using that blending option. So a quick look at the temporal period climatologies that are available to forecasters in AWIPS. We have our standard synoptic time. Forecasters can choose 3, 6, or the 12-hour forecast, depending on their confidence and also the day forecast that they're going for. But what's been added this year is the ability to have statistically significant hourly pops. When you actually do these climatologies, just straight hourly pops, the probabilities are pretty low on any given 1 hour period. And the weather services need to go to 1 hour pops, especially days 1 and into 2 for aviation forecasts and a variety of other system support reasons. So what we came up with was this hourly running period in order to get something statistically significant and high enough temporal resolution to make that possible. So the way the running probability works is it's centered around a particular hour. So the 20Z forecast or 20Z hourly forecast will have input from the 18, 19, 21, and 22 Z forecast. So you're doing an hourly forecast, but you're looking at some of the surrounding hours for influence into that probability. So the 21Z forecast would incorporate 19, 20, 21, 22, and 23, and so on. So we have 5-hour running and 3-hour running probabilities that the forecaster can also use, and this has made a big difference in being able to have hourly pops that make sense to users in terms of probability in a temporal plate. So let's look at an example. This is the regime 1 light and variable flow hourly 5-hour running hourly forecast for the state of Florida. And the day goes from 60 to 60. So as you go forward in time, starts out pretty quiet, but you can see the morning, this convection erupts along the west coast of Florida and then migrates inland, maximizing in the late afternoon and early evening across the central part of the peninsula or down the spine of the peninsula. And this is a very high resolution, both spatial and temporal way of looking at this. And it's best suited for days 1 and 2. You wouldn't want to use hourly forecast pops really beyond day 2, just due to confidence levels. Here's another example. This is the same thing we're looking at, but now for regime 6, the southeast to south flow, where we have the probability maximized along the Florida west coast during the late afternoon and evening hours. And you can see the utility here of being able to very accurately depict where the rainfall probability is very high for a particular hour and where it's quite low in different places across the peninsula. You know, the old adage that it rains at 3 o'clock 50% of the time in Florida in the summer it certainly isn't true, and it certainly shouldn't be our forecast. Here's an example at same regime 6 for a 6-hour synoptic forecast. So looking at 6 to 12Z, 12 to 18Z, 18 to 0, and 0 to 6. This is best suited for a little bit later in the forecast period, maybe days 2 to 4. And finally, looking at, say, the same regime, but a 12-hour forecast looking at 0Z to 12Z and 12Z to 0Z. This would be best suited for the extended part of the forecast to the days 4 through 7 period, when it's more of a planning forecast. You're just trying to determine, what days might be better for certain things as opposed to getting forecasts down to the hour. So we did some verification of all of this during the summer of 2020. And what we have here is a reliability chart with the percent of grid points receiving rainfall on the bottom and the percent of grid points forecasting rainfall on the vertical axis. So if we're just, for instance, looking at if the Weather Service was forecasting a rainfall probability of 30, if the climatology was forecasting a rainfall probability of 30 to 40%, then the percent of grid points receiving rainfall was about 35%. So that's not too bad. The perfect line is right down the middle there. And in general, the verification was within about 10 to 15% of the perfect forecast, which is a really good starting point when you're talking about something as complex as the Seabreeze thunderstorms. Now, the summer of 2020 was actually a fairly dry summer in terms of days receiving rainfall in any one location. This was due to significant intrusions of Saharan dust, the Sal layer, moving across the Atlantic. So it's not surprising that the forecast or the climatology had a slight wet bias on what actually occurred last year, since we're looking at an 18-year climatology and that was a drier year. So as long as we keep up with this type of verification, the forecasters can certainly make adjustments to those climatologies up or down based on what they're seeing in other variables of the atmosphere. This was day 1, and here was day 5. Some slight differences here and there, but generally under 10% or less towards the perfect forecast. So we'll go through some decision support examples now that utilizing this data. We'll start with Pinellas County in Florida. So on the west coast of Florida, Pinellas County, for those who don't know, is kind of it's a peninsula essentially. So it has water on 3 sides. So under a regime 1 flow, where it's very light and variable, sea breezes from the Gulf and Tampa Bay are able to form and all move inland towards the center of the peninsula. And what this does is allows the first storm of the day, almost always on these regime days, develop with about 30 minutes of noon, 11:30 to 12:30 roughly, with a pretty high degree of confidence right in the middle of Pinellas County. It's actually called the Pinellas County storm. And what these data sets have done is allow us to instantly provide that spatial and temporal detail in our forecast grids, where normally it would require considerable time and effort by the forecaster to draw in that type of precipitation probability detail and do it hour by hour by hour. But here it'll put that detail in as a first guess, and the forecaster can bump it up or down just a little bit based on some of the other factors in the atmosphere that day. But it really gives you a good first guess and something that we've been adding to our forecast manually for quite a while. It no longer needs to be done that way. Here's another example. It's also a regime 1 day, but just going a little bit further south, looking at Manatee and Sarasota counties in Florida. So in this case, we are looking at 20 Z in the afternoon, so 4 p.m. in the summer. And the rainfall potential and like I said, the resulting lightning threat along the beaches of these 2 counties is 10% or less. However, if you go inland, only 20 miles, the rainfall potential and the corresponding lightning threat is now approaching 60%. So you're talking about a very, very tight gradient in precipitation potential across a very small area, an area that in some cases is less than some model grid points. So the advantages for decision support and outdoor planning for something like this cannot be overstated. Simply asking the question, is it safe to go to the beach today? If you're looking at the forecast for tomorrow and it's a regime 1 day, would you rather go to the beach that day, or would you rather go look at the gators at one of the inland state parks? Well, in this case, you're much safer, and you're much safer bet to hit the beaches that day. So again, there's a lot of decision support capabilities here to provide to emergency management, the public, and any outdoor planning that needs to be done. Yet another example, looking at a 12-hour forecast for regime 6 day. So again, this would be more of the extended forecast, days 4 through 7. If you're trying to figure out what you might want to do, or you get a wedding coming up, if you look at the beaches of Southeast Florida, Miami Beach, for instance, the total daytime rainfall potential, the corresponding lightning threat here, is 25% or less. But not a long way away. Just go across Alligator Alley over there to the southern part of the peninsula. This is not a wide part of the Florida peninsula. And around the Naples area, you have a daytime rainfall potential and corresponding lightning threat of 80 to 90%. So again, huge differences in the forecast across a fairly small geographical area in a completely different decision support mind frame that you would have from one side of the peninsula to the other. And just some neat artifacts that come out of these type of climatologies due to the southeast flow here. You can notice a Lake Okeechobee lee side rainfall shadow into some of the counties there, southern Highlands County. And there are some sugarcane plantations in this part of Florida. So from a terms of irrigation and agriculture type of things, knowing these type of probabilities and knowing if you're in a long period of southeast flow that you may not get much rainfall when areas around you will, can be very advantageous. And this is the very last one of these that I'll show. It's just another example of kind of a beach forecast in Southwest Florida around Fort Myers, where with a regime 6 day, very high probability between 2 and 8 p.m. of having your beach day ruined by thunderstorms and lightning. Well, during a regime 4 day, the rainfall probabilities are coming down towards 10%. And one thing you know with these flows, when the storms develop, we also know which way they're going to develop. So certainly, if you're looking ahead for the weekend and you want to go to the beach in this area, you're looking for a regime 4 day as opposed to a regime 6 day to make your day better and safer. So knowing this type of data, we've been able to produce some high impact decision support through social media over the last few years. Some pretty high resolution temporal forecasts for different thunderstorms. Here we obviously have a regime 1 day. We're talking about a particular threat during the later afternoon down the spine of the peninsula. And here's another one with a regime 6 or 7 day where conditions are quite nice in the early afternoon along the Florida West Coast, Tampa Bay, lots of people out boating, but we're trying to let people know that the skies can be deceiving. It may be beautiful now, but within a few hours, there's going to be quite a bit of thunderstorm activity in the area and rolling offshore. So kind of giving this advance notice to let people know that they might want to end their boating days or their boating day at 2 or 3 in the afternoon and get to shore before it starts getting dark to the east has certainly been useful and gotten a very good response. So we'll finish up here by taking a quick look at the public and media way that we're going to present this. A lot of this research came out of the media wanting different aspects of different information about the wet season here in Florida. It's very important, both to agriculture and outdoor activities. So this is a website that was created. It's about 95% done at this point. We're going to roll it out officially at the end of this month or early April with some of our wet season activities that we have each year. But go over some of the features. All of these climatologies are available here. You can choose. We have 2-dimensional imagery. Choose any of the regimes that you want. So choose one of the 8 regimes, and also choose the area you'd like to look at. Anything from the southeast United States down to Florida, and also to any of the 6 varying National Weather Service county warning areas that cover Florida. And you can choose any temporal period you want with scrolling animations available. We also did point data across the state. We literally coded in hundreds of points, locations, towns, cities, and tourist attractions, things like that, and did the statistics for each one of the regimes. So in this case, we're looking at a 24-hour probability of rainfall for the city of Tampa, so you can see which regimes are wetter and which ones are not. It's one regime, one color. If we go this is all for Tampa. This is the 12-hour forecast. So we have 2 bars, one color. So the green is the regime 1 forecast for 8 p.m. to 8 a.m. and then 8 a.m. to 8 p.m. So each one of the regimes is, so you can kind of see the difference between night and day here. When we go below 12 hours, we switch over from bar to line charts. So, and the line chart is a very useful diagnosis, useful for diagnosing preferred days and times for sensitive weather. In this particular situation here, we can see that a regime 2 has a very close peak rainfall probability to regime 7, but it occurs at a much earlier time in the day. So very good for planning purposes. Florida Light and Power, which is a major utility company here in Central Florida, has requested data access in order to schedule and position field crews for storm-related issues using this data. Another example is the Southwest Florida Water Management District has requested access to the data for their decision support purposes related to agriculture and water releases from Lake Okeechobee, et cetera, et cetera. And the other part of this, we had specific requests from our media partners for information on the start and the end of the wet season. Everybody wants to know when's it going to start, when's it going to end, because that, you know, it makes such a big difference in the forecast in how we live our day-to-day lives. The problem is it's not static across the peninsula. In fact, it changes dramatically from north to south in terms of timing and intensity. So what we did is we went and we calculated some statistics on the daily rainfall coverage of the county for each day of the year. So here we're looking for Lee County, which is where Fort Myers is. This is the median daily rainfall coverage, percent of the county seeing greater than 1/100 of an inch of rain. And it actually, there was a lot of very small details that came out of this. We'd heard grumblings that often it seems like the rainy season gets started in mid-May, and then you think it's going and it stops for a couple weeks and it starts again. And it was hard to tell whether that, you know, is that a real occurrence, or is that just our perception of how things are going? But when we actually looked at the data, it does seem that there is a signal for kind of a false start to the wet season in South Florida in many occasions. This is where we kind of get into the atmospheric conditions where we're getting these thunderstorms, and then we sneak in a very late season funnel system that drives us out for a week or two before the real wet season kicks in and gets going. So that was interesting to see that perception was actually true. So we did this both median and mean. The mean allows a little bit more of the noise to get in there, but it still has a lot of utility. But generally, I prefer to look at the median values because they stick out. When the wet season really sticks out here. And the last thing I'll show is, because this was a media request, we didn't just do the counties across Florida. We did the statistics for each one of the media areas as well. So here we have the Orlando media statistics with the map on the right showing what area these statistics were calculated for. So all this will be available probably within the next month out on the web. So with that, I'm going to end this presentation. I want to thank you for your time and attention. I had a good time presenting this, and I guess we'll open it up to questions. Thanks again.
Yeah, thanks, Brian. Excellent talk. Lots of stuff to chew on there. So now, if you would like to ask questions of Brian, please do so by using the raise your hand feature in the GoToWebinar or typing in your question in the chat box. I'm going to start out with a couple. You mentioned that, you know, the lightning is a critical decision support factor. So, but what you presented is purely based on the precipitation from MRMS?
It was stage 4 hourly radar engaged.
Right, on the radar, dude. But so So are you considering a similar approach with just CG Lightning?
Yes, that would be definitely something we could do. If it's very similar studies have been done at Florida State University looking at just lightning in the late 90s and early 2000s, and you look at the patterns and they're spot on. They use the same flow regime essentially. As I said, this flow regime thing was first defined by NASA in the 60s and 70s. So they used very similar flow regimes. The only thing they did was the location that was the center of the flow regime world at that point was Tallahassee as opposed to Tampa Bay. But looking at the same southeast flow versus easterly flow, they're highly correlated. As I said, it's very rare that we get convection here that doesn't at least have some, not that almost all of it has lightning, it all has lightning threat. So in terms of decision support, there's a very strong correlation between the two of them.
Okay, yeah, makes total sense. The other thing I was going to ask about was the fidelity in the regime. So you can't adapt the regime on the fly. I mean, it's kind of a pick 'em, and then if the regime changes during the forecast, you have to adapt somehow.
Yeah, that's always a drawback. If what you could do would be a little bit more manual aspect there, but at that point, what you could do is you define the regime yourself, and you could pick different parts of the day and change it. Luckily, because of where we are in our latitude, we don't have very rapid changes in synoptic pattern here in Florida in a 24-hour period. It can happen. It certainly can. Usually, if we have something that's changing that fast, the ridge is not the dominant feature, and hence it wasn't included in this, and we wouldn't be using these tools on those days. These are for your classic summer, your majority of summer days, but when it's really classic, the regime is kind of steady state. In many cases, it will hold in one place for multiple days. But if you did need to make a change and you wanted the second half of your day to be another regime, you could just do it. Just pick the regime manually that you wanted for the second half of the day. So that's why we added that.
Right. So one more follow-up from me anyway is the nonlinear effects of the boundaries from the previous day convection. So you've got an example of boundaries, right? Looping right now, and so I presume that what may happen is that in the early initiation phases, things may form in slightly different areas, but by the full afternoon, the dominant sea breeze and boundary layer flow has basically taken over, and your climatology works well at that point.
That's exactly right. Because not only are you focusing your updrafts and your upward motion along the sea breeze due to the synoptic flow, you're also focusing it with convective outflow. So you're favored on the side of the storm that is opposing the synoptic flow. So after that first round of storms, you're really forming in a climatological sense in one direction or the other across the peninsula. Because of that, you're favored on one side of the storm, and you're actually decreasing the outflow convergence on the other side of the storm.
Okay, great. So John, do we have some questions from the audience?
Sure. We have Frank Alsheimer, and I'm going to unmute him so he can ask his question. Go ahead, Frank.
Hi, Brian. I've got a couple of quick questions, actually. First, how does the output from the study which you do, which I really like, compare to things like the HREF and some of the high resolution guidance that you already have in there?
Yep. The HREF has its days and has its goodness and its bad days. We have found that oftentimes what's going to happen with the model is they convect too late and they go way too long, and they continue stuff too late into the nighttime. So you're unless you want to make a significant shift in your timing, they can throw you off course. A lot of them, and I don't know if this is something it has to do with the radiation schemes and how fast things are warming up, but they tend to be several hours too late in getting things really going, and they end up having their storms go until the middle of the overnight period, which is fairly rare. So that's why we didn't pursue that. We did quite a bit of research into that, looking at high-res guidance from a neighborhood probability methodology, all that type of stuff, and we got limited success, but nothing as worthwhile or useful from day to day as what we've seen with this.
Okay, the other question I had is related to the website that you're going to open up at some point. How are you all going to message the fact that, for instance, when you use your like 5-hour time lag, those pops for the individual hours are still less than what you're going to have in, say, a zone forecast or something like that. This is something, that honestly, I think the whole Weather Service has got to come to a conclusion about how to deal with that. And so I'm kind of curious on your end, how do you see messaging those seeming inconsistencies?
Excellent question, and the next part of this research cycle is what I'm going to answer for that right there. Yes, there is certainly, that is a problem. It's a problem across the board in terms of how the way we do pops in the Weather Service to start with, where it's truly not a statistical pop. 60% in the morning and 60% in the afternoon is not 60% from a statistician's standpoint. What I'm looking into now for this is a similar. One way would be to utilize the weighted blend of the MBM and try to bump things up that way. But the way the MBM has been looking at what I've actually been doing this way is with the precipitation probability index. So actually scaling up those hourly pops towards, say, your 12-hour pop, where it is the most likely hour to have rain, and taper off how much you bump those pops up as you get further away from that maximum period. There's been some work done by Ted Ryan, the Sioux in Fort Worth, on enhancing and increasing our accuracy of pops using the precipitation probability index for MBM, and we're thinking about doing something very similar with this, where we can figure out when the most likely hour is for each grid point during a particular regime, and then utilize some of the longer temporal climatologies to bump those hourlies up in a statistical way that's still relevant. Does that make sense?
Yeah, no, appreciate the answer. Thank you.
Thanks, Frank. John, do we have other questions? John?
Sorry. Yes, I unmiked Dennis, so he's capable of asking his question.
Okay. Hello, can you hear me?
Yes, Dennis, go ahead.
Okay, this is more about like what exactly is required to define a regime. I know you started talking about it with Steve earlier, but like, does it have to be in place for a certain number of hours or at a particular time? Because I would imagine that the regimes might change over time. Is 3 hours enough? Does it have to be in place for 6 hours, especially with regard to like, not just the forecast for the day, but when you compiled your statistics, like the days with regime 1, 2, 3, 4, which of those days, you know, okay, now it's going to count as a day. What's required for that?
Well, the days are defined as 60 to 60, which is basically what we look at as a consecutive day. We're usually still going with convection from the previous afternoon into the evening hours, and generally done by midnight or 1 a.m. So we define the day as 60, and 12C is we have it's kind of a little bit in the middle of that. You'd be surprised how slow our patterns evolve here in the summer. It really isn't. We haven't found an issue with the regime has changed 3 hours down the road, or even 6 hours down the road. The convective pattern gets started with the earliest morning type stuff, and once you get it going, it's been defined, and the synoptic flow is not going to change very much in that period. So we actually haven't had that problems with the flow regime changing during the day. However, given that that observation, we could certainly have it not be a single hour, but have it look at a period of time to find the regime. He says we're looking out into the future for a forecast. We could look at a 6-hour period and do the same thing, and we might do that in the future.
So I think you're basically saying that the regime usually gets established by the morning and usually stays in place for the whole day, the whole forecast day.
Yeah, the regime is synoptically driven, and the synoptics at this latitude during the summer, just when we're talking about the subtropical rig itself, they just don't change that much in a 6, 12, or even 18-hour period.
Okay,
Thanks.
thank you.
Yeah, thanks, Dennis. John, do we have another question?
Sure. We have Kevin Rodriguez, and he's at WFO Melbourne, and has a question about regime 6/7, and he asks, with southeasterly flow, that's regime 6 and 7. Was there anything that indicated a significant difference between straight southerly flow and direct southeasterly flow? And then he comments, on our side of the peninsula, we noticed that even a slight difference in the flow towards the southeast can lead to a much drier condition along parts of the coast, for example. Just wanted to get your thoughts. Thanks.
I agree 100%. If you go, the further you turn that wind to the east, you decrease your convergence along the east coast sea breeze, and you propel it inland faster away from the coast. So that'd be backing. The further you back that wind to the east, you are going to decrease your rain potential on the coast. In that case, you might, if you're looking at a forecast grid, that could be something where an option could be introduced where maybe you blend a regime, or you might have a lower pop with some model guidance that you can blend it with to bring that down. But yes, you are gonna decrease your rainfall probability along the coast, especially the Melbourne area there, because of that bathymetry, not bathymetry, but the shape of the coastline there. The further you back it, it's just going to drop like a rock, especially right at the beaches. We would have loved to have done 16 different, compass sectors, but it gets to be almost too much. But we can look into ways to maybe blend some of the regimes together for forecasters.
Okay, thank you. I've got a couple of follow-ups. So on the topic of like specialized guidance coming out of this, what I'm talking about would, I think, require you to go into the lightning data sets, but have you considered like using this approach to come up with time of first CG, for given location, and conversely, all clear time for a given location? I presume those are kind of for beachgoers or boaters. Maybe they want to get out and enjoy the beach for a few hours, but if you tell them, there's like a 90% chance of a lightning strike at 3 o'clock, so they can kind of a window to enjoy their day at the beach and then get the hell out of there.
Yep. First strike lightning research has been a focus of ours for a while. We're actually, right now, I'm in the middle of a comet project with a group at Embry-Riddle University looking into first strike climatologies and messaging and some sort of a tool set to aid forecasters in that. So that is an ongoing comet project right now.
Okay, perfect. And the other thing I'm curious about the use of this for, warning ops. Is it help in preparing, the staff for a day to focus on this and get them centered on, where to look and when to look?
Absolutely. If we're going to have severe, obviously our severe weather season is actually not the summer, even though that's our thunderstorm season. It seems counterintuitive, but we have no shear. We certainly, you can consider water spouts and things like that, but most of our thunderstorms are generic false. A lot of lightning, heavy rain, gusty winds, but not severe. If we're going to see severe weather or significant water spouts, it's going to be in a regime 6 or regime 7 or regime 1 situation. That's when the sea breeze, when we have our maximized sea breeze convergence here on the West Coast, and usually, especially with a 6 or 7, it's later in the day, and we have a defined collision with the East Coast sea breeze over on our coast, and all the whole potential of the day in terms of heating is released at once. So those are our most intense thunderstorms, whereas regime 4 and 5, we're wet, but we have a flow off the Gulf, and it's considerably lower topped type convection and much less risk. So we will staff based on the regime during the summer, and it would be exactly the opposite for other parts of the peninsula where regime 4 or 5 is more likely to have severe weather late in the day, whereas as opposed to us. So yes, it's being used for staffing models. It has been in our area for several years now.
Great, thanks. John, do we have other questions?
No, we don't. Not at this time.
One other follow-up, Brian, is on the question of like onboarding new Mets, interns, whatever, using this to kind of train them up on Florida convection, and I'm assuming this helps quite a bit.
Absolutely. It's one of the first things when somebody comes on during the warm season, which is a good 5-6 months of the year around here. It's thunderstorms and tropical, and so we've got to get them spun up on sea breeze convection because it's what they're going to do on a day-to-day basis. During the summer, for day after day, we're radar shifts. We may not be issuing warnings, but they need to be watched because they can get bad. So in terms of getting new employees, they need to be on board real fast, and we use this as a training tool.
Perfect. So I think we're almost out of time. I want to thank you, Brian. Really great work, and the staff down in Tampa Bay. I think this has really been enlightening. A lot of hard work and a lot of follow through, because I know you can sort of get into this and then I'll be overwhelmed with trying to finish it up. But to make it into a fully fledged tool and visible and used on a web page, that's a lot of work. So kudos to you, and I'm glad you get the support from Southern Region and from your MIC to carry out this. And so great work, and thank you so much for presenting it.
Really appreciate you having me. It's been a lot of fun. Thank you so much.
Excellent. So with that, I want to thank everyone for attending. I said this is the March edition. It actually is the February edition of the VLab Forum. But coming up in not long from now, on March 18th, we have a topic about the NOAA USGS 3D geoelectric field model, which is the application of space weather brought down to Earth by Dr. Chris Balch of SWPC out in Boulder. So make sure you tune in for that one or watch the recording after it's done. And then coming up in May, we don't yet have an April topic. We have NBM NDFD verification being presented by Dana Strom and John Wagner. This is a new capability developed in MDL to help forecasters look at verification of the blend vis-a-vis the NDFD and gather insights for that. And it's going to be used to help support the upcoming QPF CFP demonstration that's part of the Evolve project. So with that, I want to thank everyone, and we will see you in a couple of weeks. And John will let us know when the recording of this is uploaded to the VLab Forum webpage, and you can watch it again or share it with your colleagues. So thanks, everyone.
Thank you.
Have a good one.